ever spend like an hour hunched over a Rubik's Cube, just twisting and turning, and it feels like you're getting absolutely nowhere.
Yeah.
But the funny thing is, we know a solution exists.
Right.
But there are just so many combinations. It's got to be billions upon billions of potential combinations.
Yeah, it's a classic example where the search space is just astronomically vast. All those potential combinations, right?
It's mind-blowing. And it's kind of why we turn to algorithms in the first place, I guess, to be our problem-solving GPS.
Yeah.
And one of the popular ones that I know a bit about is a search algorithm.
Exactly. You can think of A as meticulously planning a route through a city, but instead of just picking random streets to go down, it uses something called a heuristic function.
Heuristic function.
Yeah, so it sounds kind of intimidating, but it's actually much simpler than you might think.
Oh.
It's basically A's way of kind of making an educated guess about the distance from its current position, so its current state in the search, to its destination, so the solution.
Yeah.
And what this does is it helps A prioritize which paths to explore first. So it makes it a lot faster than, say, randomly trying every single combination.
So it's kind of like having that bird's eye view of the city map and being able to choose streets that seem like they generally lead in the right direction.
Precisely, yeah. Making smarter choices as it goes.
So even with this clever strategy, like you were saying, with this vast number of combinations, imagine A, trying to navigate a city with billions of streets and roads.
Yeah.
It'd just be almost impossible, or at least it would take forever.
Yeah, it becomes computationally very expensive, takes a lot of computing power, a lot of time.
And that's where this deep dive comes in. We're looking at a research paper about how to navigate these massive search spaces more efficiently, even when they make a Rubik's Cube look, tame.
Yeah. And that's no exaggeration. The researchers in this paper, they actually used a Rubik's Cube as one of their problems. But instead of the usual 12 possible moves you can do on a Rubik's Cube, they actually explored a version with 1,884 possible actions at each step.
1,884 moves. I can barely handle the standard version.
Yeah.
So how did they even begin to tackle that? Did they need like a supercomputer the size of a building?
Right.
Yeah, that many options would overwhelm even like the biggest supercomputer out there, wouldn't it, if it was trying to do it the regular way?
Right, exactly. Trying to brute force all the different combinations. But what if instead of trying to, like you said, evaluate every single move one by one, what if we could teach an AI to kind of grasp the entire problem, like see it all at once?
Okay, so like giving it some sort of superpower, like it can just teleport to the solution or something.
Yeah. Like instead of getting bogged down in each twist and turn of the Rubik's Cube, imagine if it could just develop this intuition about the most promising sequence of moves from the get-go.
Okay.
And that's actually where these things called deep Q networks come in, or DQNs.
DQNs? I feel like I've heard that before. Does that have something to do with like how AI learns to play games?
It does. DQNs are a specific type of neural network, and they learn through experience. So in this research, they basically train these DQNs on a massive data set of Rubik's Cube configurations. So like different states of a scrambled cube and the solutions.
Okay.
And over time, what happens is these DQNs, they start to learn to associate these different configurations, these states, with like how close they are to being solved.
So it's almost as if the DQN starts to get a feel for the Rubik's Cube. Like it understands that certain patterns are better than others without having to actually calculate every single move.
You got it. It's less about brute force calculation and more about intuition, kind of like, a chess grandmaster.
Right.
Who can just look at a board and just make these really strategic decisions almost instinctively, right?
Okay.
So they have that intuition.
So these DQNs, they have their little grandmaster intuition hats on.
Right.
And that's basically the key to this whole Q-star search thing, right?
Absolutely.
Yeah.
Q-search, it basically combines the structured guidance of the A that we talked about earlier with the learned intuition of a DQN.
Okay.
So remember how A uses the heuristic function to estimate the distance to the solution?
Right.
Well, Q takes that a step further, and it uses the DQN to actually learn an even better heuristic function.
So it's like we're giving our trusty A algorithm like a serious upgrade.
Exactly.
Instead of just a basic city map, we're giving it, real-time traffic updates, maybe some shortcuts, maybe even a helicopter for those really, really bad traffic days.
That's a great analogy, yeah. And the results are, as you might expect, quite impressive.
Okay, enough of the build-up, though. Like, how much faster are we talking? Give me the numbers.
Yeah.
Okay, lay it on me. Just how much faster is this Q-star search compared to, our old pal A?
All right, so get this. Remember that ridiculously complex Rubik's Cube we were talking about?
Mhm.
The one with 1,884 possible moves.
Yeah, the one I'd still be stuck on, probably.
Well, Q-star search solved it a whopping 129 times faster than A.
Seriously?
And not only that, but it also used significantly less memory, like way less.
How much are we talking, like half?
Think about 100 times less memory.
100 times?
Yeah.
That's insane.
Yeah. It's a pretty remarkable improvement.
So it's like going from, I don't know, like a bicycle to a rocket ship or something. But okay, so we can solve a Rubik's Cube really, really fast. What does that mean for like the real world? Can Q-star search actually make a difference in solving, real problems, not just puzzles?
That's the most exciting part.
Really?
Absolutely it can. Think about any field where you're dealing with these massive, complex search spaces, like drug discovery, for instance.
Okay, yeah, that's a big one.
Developing a new drug is essentially this like huge search problem, right?
Right.
Where you're trying to find this one specific molecular combination that does exactly what you want it to do. You're basically looking for a needle in a haystack, but the haystack is like the size of the universe. So imagine, instead of researchers having to like painstakingly test countless combinations in the lab, Q-star search could help them zero in on the most promising candidates right from the get-go. So it would speed up the entire process.
Oh, wow. So that would be revolutionary for medical research.
Absolutely. And it's not just drug discovery. I mean, you can apply this to so many different fields like materials, science, maybe designing new materials with specific properties, or financial modeling, even artificial intelligence itself, right?
Oh, wow.
Anywhere where you have a massive search space, this could be a real game changer.
That's incredible to think about. So like we started with a Rubik's Cube and now we're talking about like revolutionizing all these industries, and it's all thanks to AI. Like when you think about it, it really highlights just how powerful AI is becoming.
Yeah, absolutely. And this is really just the tip of the iceberg, I think. This research gives us this little glimpse into the future of problem solving, a future where AI isn't just, helping us do things a little bit faster, but it's actually allowing us to tackle these challenges that we previously thought were just impossible.
Right. Like we're witnessing like a whole new era of problem solving. And I don't know about you, but I'm kind of curious, like what impossible problem will AI crack next?
Yeah.
What new frontiers are out there just waiting to be unlocked? That's something to think about. So listeners, that's our deep dive for today. Hopefully you're leaving with a sense of awe and maybe a little bit of excitement for the future, because I know I am. And remember, keep exploring those big questions. Keep that curiosity alive. Until next time.